Hello everyone, this is the Fliggity Fish and welcome to Fliggity Fish Physics. Today we're going to be taking a look at some practice problems from the, uh, what is it called? Work energy rotation thing. So first of all, let's look at a pretty common one. Let's copy and paste this. That won't work. I'll just snapshot the snapshot. Okay. Okie dokie. So here we have an Atwood machine and it's pretty much asking us to use there's a pulley, a solid sphere, so that means we know beta is equal to 2/5 um with a mass of blank and radius. So let's just call this big M and R. We can call this M1 and this is M2. So there's no friction between the 8.9 mass and the horizontal surface, so this is frictionless. And the rope does not slip on the pulley, which means we can apply the V equals R omega and A equals R alpha formulas. So let's get to work. The system is released from the rest. Use work and energy principles to determine kinetic energy. Okay, so first of all, what's going to happen when we let go? It's going to go whee down this way. So um, let's solve it symbolically. What is our system? We gotta define a system for work energy. So I like to put everything inside the system. So we're gonna say the Earth, because I own the Earth. Um, the masses, like all three of them, M1, M2, and big M, as well as the pulley and the rope. So there's literally no external forces acting on the system. As you know, the big formula is that external work is equal to the change in energy of the system. So work external is equal to 0. What's gonna happen when this thing starts moving? Well, the pulley's gonna start rotating, the block's gonna translate, and this block's gonna translate. So pretty much what's gonna happen is all the gravitational potential energy this thing has is gonna turn into rotational kinetic energy as well as translational kinetic energy. So we can say that delta UG plus delta K rotational and delta K translational. So let me get out the little pieces of paper I did the work on already. Oh well, I think I left it downstairs. So well, the change UG has it's already given. So like the distance that this moves, the distance that this moves are gonna be the exact same because the rope does not stretch. So we can say that mgd, because down is positive direction, d final is, uh, let's say this is 0, it moved d, um, plus rotation, which is just going to be the pulley, which is 1/2 I omega squared, and the translational, so it's going to be 1/2 m1 v squared plus 1/2 m2 v squared. The reason that the v's are the same is because due to the rope not stretching, they're moving at the same speed. Um, so now, what do we know here? We know M, we know G, we know D. We know I, we can find that because I is equal to beta mr squared, and we know this, we know this, we know this. We can convert omega into V over R, and then we can factor out V, and then we can plug it back into the formula. So I'll show you how we can do that real quick. So, first of all, we can just say I is equal to beta mr squared. This is equal to v squared over r squared plus m1 v squared plus m2 v squared, and we can just factor out a 1/2 because all three of them have 1/2, and then mgd. So all the gravitational potential is going to turn into kinetic, so the magnitude of this is going to be equal to this. So what do we do? Well, we can try to factor v out too. So 1 half v squared. This goes away, this goes away. These two cancel out, and this goes to the front. So beta m plus m1 plus m2. So to find the velocity is going to be equal to 2 mgd divided by beta m plus m1 plus m2 square root. And once you have V, you can plug that back into the kinetic energy formula of 1 half mv squared if it's asking you for the kinetic energy of a mass, which for here it does ask for the 4.3 kilogram mass. And if it's asking for the pulley, you can just plug it back into 1 half I omega squared. So yeah, that's the first question. Let's get on to the second question. Okay, so we have a system right here where there's a spool and it's letting out string, so it's going wee, and then there's a force that's pulling on the string or steel cable, and there's a constant force that's pretty important, and cable, and we know the masses and the radius of each of them, as well as the moment of inertia for the pulley because it's not uniform. Okay, so let's say the system. What is it gonna be? I like putting everything in, so let's put pulley. Oh my gosh, my brain cells are fried. Oh my gosh, my PC is also dying. Pulley, spool, and I guess the cable. Okay, and the earth, if you want to say that. So the work external is equal to the change in energy of a system. But oh whoa, in the system, this force is not included. So that means force times the distance. I th force times distance. I think it's sine theta, but sine theta. This is is it cosine theta? Pretty sure it's cosine theta. Cosine theta, but this is equal to 1 because it's the cable's moving in the direction of the force. And that's going to be equal to the change in kinetic rotational energy because nothing's really translating. It says right here that they're mounted on frictionless axles that run through their respective axes, and that um, it's not translating. I'm pretty sure it says it here. Eh, well, I guess we can just assume that. So FD is equal to 1 half I omega squared of the spool plus 1 half I of the pulley omega squared. Okay, now that we know this, we can factor out some common stuff. First of all, we can say, oh, there's a 1 half in front. And the I of the spool, it says the spool can be considered as a uniform cylinder, which means that it would be beta mr squared. But in this case, beta would be 1 half because it's a cylinder. And then omega squared is the same thing as v squared over r squared. But the thing is, r depends on the contact point. So for the omega of the spool, right here, it's going to use this r right here. So let's make it a capital R. So boom, boom, this cancels out. So you'd be left with 1/2 beta m v squared. And after that, do the same thing to this side. But this time, they give us the beta. It's 0.45 for this one. So let's just replace this with a 1/2 and turn this into a 1/4 mv squared plus a 1/2 times beta mv squared as well, because the radiuses are going to cancel out respectively. It's equal to ft. So once we do that, what we can do is just say, oh, if we want to find the kinetic energy, we have to find the velocity of the cable. So, big brain. We're just going to say that 1/4 m. Wait, no, we can factor v squared out because it's the same. So v squared of 1/4 m plus 1/2 beta m, and these are different m's by the way, is equal to ft. V is equal to ft divided by 1/4 m plus 1/2 of beta little m. Let's just change it and root. So once you find the velocity, magnitude, or speed, you can find the kinetic energy by plunging it back into the kinetic energy of a rotating object. Pulley or spool, omega squared. And omega can be replaced with v squared over the r or little r. So yeah, you'll have the information right here. You got this, you got this, you can find k. Okay, next problem, and I think this is the last one I have. Okay, so what's going on in this system? Well, this mass is falling, and this system is rotating about this axis. So, let's go set our system. Our system is going to be the mass, the Earth, and the disks. Also, if I go abruptly, probably a tornado. Um, yeah, so the external work is equal to change in energy in the system. Okay, all the forces acting, there's an mg. I forgot cable or string. There's a tension. There's a tension. That's pretty much all the forces, and they're all in the system, so there's no external work. So it'd be 0 is equal to change in UG plus change in kinetic translational plus a change in rotational. Okay, so in this case, they gave us the radius and mass of the two disks that are being rotated, and they also gave us the kinetic energy of the pulley. So what did they do? The kinetic energy of the pulley is 220. So they gave us this. So what is K rotational? K rotational is equal to 1/2 I system omega squared is equal to 220. Okay, what do we know here? We can find the I of a system by using parallel axis theorem. Um, so the small disk, this is the axis of rotation. So 1/2 little m r squared, and then there's another big 1/2 big M r squared, but it's shifted over. Here's the center, so we have to find this, which is going to be little r. So it'd be plus um, big M little r squared. So this is the rotational inertia for that system. So what do? We know this. We know this. We know radius. We can find the speed of the object when it has 220 joules of kinetic energy in the rotational portion. So let's just say that v is a number, and we know it now because we can solve it with this formula. What we can do now is plug v back into this equation and see how far it goes down, because what do we know? We know um, okay, so pretty much we know this, we know this, we know this because they gave it to us. We know this, we know this, we don't know this. We can find the height. So yeah, pretty short video. It's raining, so y'all stay safe. See ya.